Your textbook never actually shows you how to connect a differential form for the rate law with the integrated rate law. If you look at the first order rate law, you can see that the negative of the change in concentration of A divided by the change in the time gives you Ka. That delta A over delta T term represents the rate. This is an average rate using well-separated times. A more appropriate way to represent a differential rate law is to use the D notation from calculus. And this would represent an instantaneous rate of change. So the gap between timestamps is very small. And what we can do is we can use integration to move from this differential form to the integrated form. And in this video, we'll do that for first order reactions and for second order reactions. So the first thing we need to do is we need to get this expression into a form that we can actually use integration on. So we'll get the terms involving the A together, and we'll move the term involving time to the other side. Now we have an expression on the left-hand side that deals only with A. The right-hand side deals only with T and a constant K. So now we can integrate both sides. And we'll do this from a 0 position to a 1 position so that we can do a definite integral. Now we have an expression with an integration on each side. And both of these are simple integrals, nothing fancy here. The integral of 1 over x is ln x, and the integral of dt, the integral of 1 over a is simply ln a, and the integral of dt is t. But because we have definite integrals, we can take that a step further. And since we're working with time on the right-hand side, the t0 term is literally t equals 0, so we can simplify this a little bit further. t1 minus 0 is just t, so we can say the right-hand side is simply kt. And if we want to simplify the left-hand side, we simply multiply through by that negative sign. And now we have something that's approaching the integrated rate law as it's written in your textbook. With a little bit of rearranging, we end up with the ln of A at some time t being equal to negative kt plus ln of the initial concentration. We can do a similar kind of thing for a second order reaction. Again, we need to convert our deltas into that D notation, but aside from that, the process is almost exactly the same. Again, we arrange everything so we end up with two different terms to integrate. And we can write that as, again, a definite integral going from a 0 position to a 1 position. At this point, it might be nice to remember the integral for 1 over x squared. 1 over x squared could also be written as x to the minus 2. So if we want to integrate x to the minus 2, using that same logic with our a term, we can find the following. We've simplified the right-hand side without showing the intermediate steps because it's exactly the same as in the previous derivation. Now we'll simplify the left-hand side term. And again, to write that in the format that is similar to the one in your textbook. And we've rearranged, and the two expressions match.